Okay, so we're going to start with squeeze theorem. Okay, so let's see if that page number is right, because some of my notes, even though I've had these books for like 4 or 5 years now, some of these, I think it's right. Okay, so this is from page 882 in your book. So the idea for the squeeze theorem is if here you see in this picture, we have some function f. And f looks like a crazy function there. We don't really know what f is. But for some reason, we see that all three of those graphs come together at that one point. Okay? And our graph G, which looks kind of like maybe a parabola there, it is always above f. Right? And then H is always below f. So if we know these things, if we know that H is down here, F is always in the middle, and G is always above, always on the top, right? We know those are the case, and we know that H and G, so the bottom and the top, have the same limit. Okay? So if they have the same limit, that means they have to go through that same point right there. Right? So if they have the same limit, then that tells us by what we call the squeeze theorem that F has to also have that same limit. Okay? Which kind of makes sense because G is always on top, H is always on bottom. If they both come together and meet right there in the middle, then F is the function in between, so it's sort of squeezed in between those. And for this to be true, that H of X is less than or equal to F of X less than or equal to G of X, then F has to also go through that same point right there. So this is called the squeeze theorem. And it can be used to find limits of functions that we otherwise would not know how to find the limit of. Right? So maybe H here and G here are both parabolas and we know how to find their limits, but we don't know how to find the limit of the crazy function in the middle. We could use the squeeze theorem for that. So it can be used to prove several different things with the trig stuff that we're going to see soon. So that is why it is in this section. So here are the types of problems that you may see. Okay? So use the squeeze theorem to find the limit as x approaches c of f of x. Okay? And they tell us c equals 2. They also tell us that negative x minus 2 squared plus 3 is less than or equal to f less than or equal to x squared minus 2 squared plus 3. Okay? So let's look at each piece here. Let's start with this. Negative x squared minus 2 squared plus 3. What does the graph of that look like? Okay, it's our blue. It is a parabola because it's got that squared. The minus 2 moves it to the right 2, the plus 3 up 3, the negative out front flips it upside down, right? And well, flip before it moves. So that is our blue graph over here. Then over here, I've got basically the same thing except for it's positive. So that's this red graph here that I've now highlighted in green. And I have no idea what f is, right? They didn't tell me what f is. But I know f is always between those two functions. So f could look like anything. It might do something crazy like this. But I know in order for this to be the case, right here, that f has got to sort of squeeze through those points. So, if I find the limit of the bottom graph, limit as x approaches, c here is 2, so limit as x approaches 2 of negative x minus 2 squared plus 3. How do I find that limit? Just plug it in. Direct substitution. So negative 2 minus 2 squared plus 3. That is going to give us 3. You can also look from the graph since I've given you a graph here, but you may not always have the graph given to you. And then we do the same thing for the green graph. So x minus 2 squared plus 3. That's going to be 2 minus 2 squared plus 3, which also equals 3. So since both of these limits are 3, we can say by the squeeze theorem, limit as x approaches 2 of f of x must also equal 3. Now, you should on these, I'm pretty sure the book is going to always give you ones where you get that same limit. If, for some reason, our limit of the yellow function was 3 and the limit of the green function was 4, then we can't use squeeze theorem because those two limits don't equal each other. So it would just be, we wouldn't be able to make a conclusion. I believe in the textbook on these problems, it's always going to give you ones that actually do work there. But this would be the work you would show if you're asked to do these. You would show that the limit of the bottom function equals a certain number, the limit of the top function equals that same number. So you would say by the squeeze theorem that middle function has to also equal that. Okay, questions? Okay, so here are the types of problems you're going to see in AP Classroom about this. So we're going to have an assignment after our quiz on Friday that is going to be in AP Classroom, and it's going to have some squeeze theorem stuff on it. And this is what AP Classroom is going to look like. The function f is defined for all x in the interval from 2 to 7. Which of the following statements is, if true, implies that the limit as x approaches 4 of f of x equals negative 5? Okay, so A says there exists a function g such that f is always less than g, and so that tells us that this limit, and we know that the limit as x approaches g equals negative 5. Does this prove that f has to have a limit at negative 5? If we know that there's a function g that's always above f. That doesn't really tell us anything, right? Because that could look something like this. G could be down here. G's top function. G could be up here, and f could be way down here, right? They don't have to touch if that's the case. So that does not really tell us anything. What about B? What do you guys think about B? It's really the same as up here, right? Except for this time, G is less than F. Does that tell us anything different than A? It does not. So the only difference here is that this time, here G was on top, F was on bottom. This time we know G is always on the bottom. We know F is up here somewhere. They might touch. It might be true, but it doesn't imply that it has to be true, right? So these two right here where we just have two functions, that's not enough to use squeeze theorem. Okay? So C and D are looking better. All right? So notice also, it's also helpful to look at your answer choices and see they're very similar. We just need to see what's different about them. So there exists functions G and H. That's the same on both of these. This is different. F is less than G of X less than H. And it tells us the limit as X approaches 4 of the limit as X approaches 4 equals negative 5. here, this is exactly the same. The only difference in these two answer choices is the order of our functions here. So we want to know about f of x, right? That's what the question is asking us about. So to use squeeze theorem, where should f of x be in that order? Middle, right? So what answer choice is the correct answer choice here? It's going to be D. Because D tells us that we've got f here, we got g is always below it, we got h is always above it, and we know, well, this is a terrible graph right here. We know here at 4 that our limit should be -5. Obviously, I need to put my axis up here somewhere, not down there at the bottom. It's a bad picture. But f is in the middle. We know both the limit of g and h give us -5, so f would also have to be -5 in that case. So that's the type of AP Classroom problem that you'll see. Questions on those? Okay. Here's a different type of problem we're going to see. On the interval from 0 to 6, the functions f of x equals x minus 3 squared and g of x equals -x minus 3 squared have the property that g of x is less than or equal to h of x less than or equal to f of x. We need to find the limit as x approaches 3 of h of x. So, h, do we know the equation for h of x? We are not given the equation for h of x, but h of x is my middle function here, right? So as long as the bottom function and the top function both have the same limit, then I can use squeeze theorem to prove that h also has that same limit. So we would do the limit as x approaches 3 of g is the bottom, so let's do -x minus 3 squared. This is just a direct substitution, so you've got 3 minus 3 squared. You're just going to get 0 there. And then we would do the limit as x approaches 3 of f of x, the top function, x minus 3 squared. Again, just a direct substitution problem, so 3 minus 3 squared would also give us 0. And so then we could say by the squeeze theorem, limit as x approaches 3 of h of x also equals 0. Now, when you are doing these on your homework, I would like for you to write it out like this. I realize you could just plug in your 3 real quick, see, oh, it's 0, and write down 0. But this is what they would be looking for if it shows up on a free response. You have to prove it, not just get the right answer. You have to show the logic behind it. A lot of times the questions will say justify your answer or explain your answer. Okay, so squeeze theorem goes in this section because there are some special trig limits that we need to know, and those are proven by the squeeze theorem. So I'm going to pull up Desmos just to show you guys this real quick so you see why these are together, because otherwise they don't really seem to go together at all. I have got the function, I'm going to say f of x equals sine x over x. Okay, so that function looks like this here. And if I look at the graph, it looks like that limit is 1, right? But just looking at the graph doesn't guarantee that that's the case. It can't prove it's the case. Looking at a table doesn't prove it's the case. It supports it. Sometimes it's like good enough, that's all I need to know, right? But something like squeeze theorem can be used here, because if I do a function like f of x equals absolute value of x plus 1, Actually, let's do, that'll work. And actually, let me call that g of x. And h of x equals negative absolute value of x plus 1. Okay? So, would you guys agree that the blue graph is always above f and the green graph is always below f? That seems to be the case here. So, by the squeeze theorem, you don't have to write this down, but what we could do is we could say the limit as x approaches 0 of absolute value of x plus 1 is going to equal absolute value of 0 plus 1, which equals 1. We could also say limit as x approaches 0 of negative absolute value of x plus 1 equals absolute value of 0 plus 1, which is also 1. Therefore, I probably haven't used this for you guys yet. Have you seen these 3 dots used like that, little triangle of dots? That is a mathematical symbol that means therefore, because mathematicians don't like words. We like symbols better, and we try to replace every word we can think of with a symbol. So if you want to use this as the word therefore, you can. I like to use it. It's shorter to write. So therefore, by the squeeze theorem, we could say the limit as x approaches 0 of f of x, which is sine x, over x must also equal 1. All right, so that is why they have put this stuff together in your unit, in your book. But as far as like actually working out the problems, it's not going to be. We're not going to have to do squeeze theorem to do these problems. So that hopefully ties those together. They seem a little disjointed, but we won't actually have to do that anymore. So these two things right here are facts. They can be proven with the squeeze theorem, but you do not have to prove them with the squeeze theorem to use them. So you want to make sure, I would probably like put a star next to them. This you need to have memorized. Okay? You need to have memorized that the limit as x approaches 0 of sine x over x always equals 1. And the limit as x approaches 0 of 1 minus cosine x over x equals 0. Similarly, that can be proven with the squeeze theorem, but we won't go through that proof there. So if we ever see this limit, we can just say it equals 1. We have memorized it. It's been proven by mathematicians before us. We don't have to prove it. We can just say that it equals 1. We can also use it to answer similar problems, such as the limit as x approaches 0 of sine x over 7x. Now, this right here almost looks like the limit that we have here, but it's not quite the same, right? So the way that we're going to think about this is we're going to think about those properties of limits that we have. Would it be okay for me to write sine x over 7x? Could I write it like this, 1/7 times sine x over x? Is that okay? If I multiply those things back together, will I get sine x over 7x? I will, right? So I could write this limit this way. Then, this right here is just a coefficient. What can I do with coefficients according to my properties of limits that we have worked on? Does it have to stay inside of that limit? It can be brought on the outside as long as it doesn't have any x's with it, right? As long as it's just a coefficient and as long as it's multiplied. So I can write it like this, 1/7 times the limit as x approaches 0 of sine x over x. Now, this stuff right here, limit as x approaches 0 of sine x over x, that is the same as this. What does it equal? 1. So you don't have to write the step, but that means we got 1/7 times 1. So what is our answer going to be? 1/7. So if we have numbers that are coefficients there, we can sort of break them apart and then pull that coefficient out front for that. All right, example 5. Now that's talking about tangent. Either one of these special trig limits have tangent in them. They do not. So it's probably not going to help me to have tangent here. How can I get rid of tangent? Okay, I need to change its sines and cosines. What does tangent of x equal? Some trig identity stuff. Sine x, not plus, over cosine x. So here's another thing that you need to make sure you have memorized. This is trig identity stuff from pre-cal. So tangent equals sine over cosine. So let's change that here. Limit as x approaches 0 of sine x over cosine x over x. Now, I do not like complex fractions. They generally do not help us do anything. So what we've got sine x over cosine x. There we go. I can treat this like it's x over 1, right? What do we do when we divide fractions? Flip the second and multiply. So we've got limit as x approaches 0 of sine x over cosine x times 1 over x, which will give us limit as x approaches 0 of sine x over x times cosine x. Now, at least I don't have tangent anymore. At least I have sine, right? But that is not one of my special limits either. But it kind of has a special limit hidden in it, right? Because right here, I've got sine x over x. I've got sine x over x. It's just I've also got that cosine over there. So when we're multiplying fractions, we just multiply straight across. We could break this back apart. Okay, so we could do this. We could do limit as x approaches 0 of, I could write it like this, sine x over x times 1 over cosine x. So I can, because everything's multiplied together there, I can take the part I actually want to be separate and separate it out from the other stuff that I don't need. If there were plus or minus signs, that'd give us some trouble, but this is fine. So, limit properties then tell me that, no, so for this one, I can't take, like I did right here with this 1/7 and just pull it out front. I cannot do that here because this has an x with it. So I can't just take that 1 over cosine x and pull it out to the front because it has a variable. But limit properties also tell me if I have two things that are multiplied, I can just take the limit of those two things separately and multiply them together. So that means I could write it like this. Limit as x approaches 0 of sine x over x times limit as x approaches 0 of 1 over cosine x. And there's popping up what we had before. Limit as x approaches 0 of sine x over x. What does that equal? That up here we know and are going to memorize always equals 1. So that's going to equal 1. And 1 over cosine x, I can actually just do direct substitution for, because I'm going to get 1 over cosine of 0. Here comes the unit circle. Oh, it's back. At 0, we're right here. That's 0 degrees or radians, either one. And what are my coordinates at 0? What is it? What are the... Think about graphing that point. What's your x-coordinate? 1. And then the y-coordinate here would be 0. Which one's sine, which one's cosine? Cosine is your x. Sine is your y. So what is cosine of 0? And you get 1 as your answer. Anybody else feel a little disappointed to do all that work and get 1 as your answer? I did a little bit. We are going to have to work on unit circle. At this point, it's mostly going to be looking at, really mostly just looking at the point where we're approaching 0. So it's not going to be a terrible problem, but we do need to know that. All right, let's look at this one. Okay, so this looks a little bit like example 4. In example 4, we had like a 7x in the denominator. This time we've got a 4 in the numerator, but it's inside of our sine function. So is it okay to just like pull that out? We cannot do that mathematically. That is not possible. So we're going to have to treat this a little bit differently. Now, what we need to know is that while we wrote down that the limit as x approaches 0 of sine x over x equals 1, it would be true that the limit as x approaches 0 of sine of anything, question mark, over that same question mark would equal 1. All right? So, if I had sine of 4x over 4x, that limit would still equal 1. So as long as these two pieces, whatever they are, match each other, I would get a 1 here. So it would be really great if I could just like do that. But can I do that? No. But there's a way I can do that. I can do that if I also multiply the numerator by 4. Is that permissible? If I have a fraction and I multiply the top by a number and the bottom by a number, it doesn't change its value, right? Because essentially I've just multiplied by 1 there. 4 over 4 equals 1. So I can do this. Now, what I've got is I've got this 4x and this 4x right here. They match. And this 4 is a coefficient. It can be pulled out front. So I'm going to have 4 limit as x approaches 0 of sine of 4x over 4x. And all of this stuff right here, that's the same as limit as x approaches 0 of sine x over x. So that stuff all equals 1. So I've got 4 over 1, which is going to give me 4. I realized that if you just took that 4 and pulled it out front, you'd get the same answer. And it would pretty much work every time on a problem that looks like this, but that reasoning would be mathematically incorrect. So, you're probably not going to have to show you work on a problem like this on the AP exam, but mathematically, we're multiplying on top and bottom by that 4, and then pulling that extra 4 out. Okay, questions? All right. Secant. What is secant? Somebody remind me, what does secant equal? Because I know we're not going to be able to do this problem with secant. 1 over cosine. So there's another trig identity popping up there. We might need to have a unit circle and trig identity little quiz sometime to remind ourselves of all of these things. And it won't go away because Jack Zamudio is taking Calc 2 at Chapel Hill, and he emailed me the other day and said, Ms. Hyatt, can you please send me those formula sheets, the one from pre-cal and from calculus, because I've realized that I really need to have all that memorized well. So it's assuming you go to Calc 2. It just sticks around. So I know I'm not going to get anywhere with secant because my special limits that I know have nothing to do with secant. So let's change this to 1 over cosine x. And in case you're getting worried, we're not going to get through with these notes. We'll just do the trig stuff. Okay. All right. So, complex fraction, we don't want to have a complex fraction, right? Fractions inside of fractions are just difficult to deal with. So I need to get some sort of common denominator so I can put this here as a singular fraction. This is a little like one of the problems we did the other day. There's 2 ways you can sort of think about it. You can either get common denominators here in the numerator and then flip and multiply. My personal favorite, though, especially when the denominators are simple like this, is just to multiply the top by that denominator and the bottom by that denominator. It'll save you a step on your simplifying. So I'm going to write this over to the side just so you guys are really clear about what we're doing, because I don't want you to be confused by it. This part would be done in your head. So we're distributing here, which means we've got cosine x times 1 over cosine x. And then we'd have minus cosine x. What would happen right here with these cosine x's? They would cancel. So we would get 1 minus cosine x. Now, I would encourage you to do that part in your head as you're multiplying. So when I distribute that cosine x here, I'm going to get 1 minus cosine x. In the denominator, I'm going to have x times cosine x. And I got the limit as x approaches 0. All right, do you guys see a special limit? 1 minus cosine x over x was one of our special limits right there, right? It equals 0. So I really want to take this stuff and split it off. So we can do that because it's the entire numerator. And then I can put that over x. And then I could write this part as 1 over cosine x. And if you're not sure if you've done it right, just think about multiplying it back, see if you get the same thing you started with. Now, I could not split it like this, 1 over x minus cosine x over cosine x. I can't split it at the subtraction sign. That would be terribly bad, right? But because this stuff right here is multiplied, I can pull this stuff away and just pull the 1 over cosine x over to the side. All right. So I can do the limits of these separately. So again, I probably wouldn't write this step, but I'm going to just to be very clear about what's happening here. We're doing limit is 1 minus cosine x over x times the limit as x approaches 0 of 1 over cosine x. Not necessary to write that step, but to be very clear what's happening, I'm going to. What is the limit as x approaches 0 of 1 minus cosine x over x? That is 0. That's the special limit. Okay? It does matter what the second limit equals, even though 0 times anything equals 0. because you want to make sure that this doesn't give you something that's undefined. Because if it's undefined, then you're going to get that the limit can't exist. But we just found cosine of 0 a little bit ago. What was cosine of 0? We're at this point right here, 1, 0. It is your x coordinate right there. So it's 1 over 1. 0 times 1 is 0. These problems can be a little frustrating because you just get zeros and ones as all of your answers. If you have to guess on a problem like this, guess 0 or 1. It's probably going to be right. Okay, questions there? Cosine is your x coordinate on the unit circle. And so this point right here, if you think about graphing this, right, your x coordinate would be 1 because you would go over 1. Your y coordinate would be 0 because you're not going up or down. And so, and that x coordinate gives you your value. Because we are finding cosine of 0, like we would plug 0 in there, so we're finding 1 over cosine of 0. And so we're looking at their 0 degrees or 0 radians. Okay? All right. Real quick. 1 minus cosine squared x. What does it equal? It equals sine squared x. 1 minus cosine squared x equals sine squared x. Some of that trig stuff is coming back. So, limit as x approaches 0 of sine squared x over x. If I have sine squared x, that just means sine x times sine x, right? So I could write it like this. Sine x times sine x over x. Could I put this over 1? Would be alright. Just multiply it like that. And for sake of time, I'm not going to write it, but if I do the limit of sine x over x as x approaches 0, that will equal 1. And then I'll have limit as x approaches 0 of sine x. So that's 1 over sine of 0. We're just using direct substitution here. What is sine of 0? It's 0. 1 times 0 is 0. Okay. All right. So this assignment, let me look at it real quick. 97 through 102 is your squeeze theorem stuff, so we're still going to do those. We need to cut down the 69 through 80. Let me see. Right there, that's going to be 77, 69 through 77. Okay, we need to do a couple things with E that I think we can squeeze it in at the beginning of class tomorrow, but we mostly got this done. 97 through 102 is squeeze theorem stuff. It's going to ask you to graph it. You don't have to draw those graphs. You can just look at it. Desmos will be easier to look at. It's fine with me if you want to use that because it's not a big thing to learn. And if there's anything we've been doing that you got questions on, I do have tutoring in the morning.